Hi, this is Benny. I've dedicated my life to understanding the universe in hopes that someday I am given the opportunity to hop on a rocket and see it for myself. Every atom in your body was created in a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it originated in stellar furnaces. This means that quite literally, the universe is in you. You are a product of cosmic alchemy, billions of years in the making. The same processes that formed galaxies also formed you, linking your existence to the vastness of the universe. Hello everyone, and welcome back to another episode of Space Bites. It's me, Benny, your favorite nerd. So it has come to my attention that even though I introduce myself as an astroparticle physics student to my friends and family, very few actually know what that entails, which is fair because it is quite a big umbrella. So to be able to explain to you how I ended up here in Zurich getting my master's in astroparticle physics, we need to go back in time to when I was just 19 years old and I had just graduated high school in Jeddah, Saudi Arabia. And it was still during COVID, so there was still a travel ban. I couldn't really leave Saudi, but I was already accepted into the International Study Center for Durham University, which means I got to do my foundation year online while I was still in Saudi. So doing a foundation year in physics meant I got to study like general subjects like physics and math. And if I got an overall average grade of 80%, then I was able to progress into Durham University the next year. This is something that not a lot of people might know. It's that when I originally applied to Durham University, I applied through UCAS, and which is like this website that allows you to apply to multiple British universities for your bachelor's at the same time. And so I'd applied to study physics at Durham, and they told me that because I'd done my A-levels when I was in high school, which are these, it's part of the British system. It's these advanced courses that you can do. And I did my A-levels in physics, math, and biology at AGS. They said because I'd done my A-levels, then I was overqualified for a foundation year. And so they sent my application directly to Durham University, so the actual university, not the center that handles foundation year requests. And they'd accept me directly into the university. And I was like, no, I know myself. I need time to adjust to new environments. For me, doing a foundation year will be more about adjusting to life in the UK, because I knew I'd have to move away to live by myself, adjust to like a new country that operated very differently from how Saudi operates. So I was like, no, I don't want this. Please put me back on the foundation year program. Let me do this. And then hopefully, because I already done all of these classes before, then I can very easily go through the classes and just focus more on myself, on living in a new country. How can I live by myself? All of these new things that I'd never experienced before. And so they transferred my application back to the International Study Center that handles foundation year requests. And I was accepted to do my foundation year at, technically at Durham University, but it is like a separate center that you can kind of go through. And so I did my foundation year for a year online, still back at home in Saudi because of COVID. But by the end of that summer, it was summer of 2021, things with COVID had kind of died down. The travel ban was lifted. And come October 2021, I was able to travel. I left Jeddah. I went to Durham. And Durham is kind of hard to access because it is quite remote. The easiest way for me to travel was to go from Jeddah to London and then take a 3-hour train from King's Cross, yes, the famous one from Harry Potter, from London King's Cross station from London to Durham. And it was about a 3-hour direct train. And it's one of the most beautiful places that I've ever been to in my life. And I was very lucky to live there for 3 years. And so January of 2024, when I realized, I was like, okay, I'm going to have to start applying for a master's soon. I'd applied to a bunch of universities around the UK to study astrophysics. It has always been a dream of mine to study engineering instead. I've always been kind of in between the physics and engineering world because physics can be very theoretical sometimes. I'm a very practical person. I like to get my hands dirty. I like to build things. I like to not only understand how the world works, but how can I make the world work for me? How can I actually spend time manufacturing stuff, bringing my vision, my ideas into fruition, and actually be innovative and be creative. And so even though I'd studied physics, which I loved and it was super fun, and it's what led me to later on study astrophysics, I was still always in between worlds. So I applied to also study aerospace engineering in London at Queen Mary University, and I'd gotten accepted. So originally that was going to be my plan. I was going to graduate from Durham with a bachelor's in physics, and then move to London in September to pursue aerospace engineering. And then the coolest thing happened. I was having a conversation with one of my super close friends, Daniel, who was my lab partner throughout my time at Durham. And I was telling him about how I was applying to master's degrees and, just about the process in general and about how I wanted to study aerospace engineering. And he told me about this university called ETH, which is, I think ETH, if I'm not wrong, is ranked 11th in the world, just in general. And it has very, very good physics program. It has a very good physics program. And he was telling me about this university, and I was like, well, that sounds amazing. Like, Switzerland wouldn't be a bad place to live in. So this idea of me studying in Switzerland was, very much so inspired by Daniel. So not only did I apply to ETH, but I applied to University of Geneva, I'd applied to the University of Bern, and the University of Zurich. And I was lucky enough to get my acceptance into the University of Zurich, and I loved this program the most out of all the cities. Obviously I did very, very intensive research, not only on like the universities, but the programs and the cities themselves as well, looking at the living cost, looking at the safety, the public transportation, all sorts of things. And I, decided to go with Zurich. And so the program that Zurich had available for physics was a general like master's degree in physics, and they have a couple of specific pathways that you can follow. Now, during my time at Durham when I was doing my bachelor's degree, I always knew that I wanted to do something in space, that, there was no doubt about that. But it was during my time in Durham that I really fell in love with astronomy and astrophysics. And, astronomy is just a more, it's more observational, I would say, while astrophysics is more theoretical. So with astrophysics, we're more focused on, for example, how do stars form, that sort of thing. It's a lot more of the theoretical aspect. Whereas with astronomy, we learn more about, like, observational techniques, about telescopes, about actual, like, the way that I view it, astronomy is just a little bit more practical than astrophysics is. When I say practical, I mean it's a little bit more hands-on. And so I applied to Zurich, I got accepted, I chose the pathway that I wanted, which is astro-particle physics. And this is where things get interesting. So, what is astrophysics? It's the branch of physics that studies the behavior, properties, and interactions of celestial objects and phenomena in the universe, such as stars, planets, black holes, galaxies, and cosmic radiation. And it applies the principles of physics to understand how the universe works. The particle part, we focus on the tiniest building blocks of matter, like neutrinos, which are a type of particle. And neutrinos are actually my favorite type of particle just because they're so funky. And I'll probably make a whole episode about neutrinos and why they're so weird, because it's super interesting. But particle physics, like I said, we focus on the tiniest building blocks of matter, like neutrinos, cosmic rays, and dark matter particles. And there's already an episode on dark matter and dark energy, and that is like, dark matter and dark energy is the best example of astro-particle physics, because again, we're looking at the content of these things. What are they made of? That's the particle aspect, and then it's something that's in space, and I guess that kind of introduces the astro aspect of astro-particle physics. We also, together, astro-particle physics helps us answer the big questions, like what is the universe made of, how did it begin, and what's happening in the most extreme places, like exploding stars and black holes. So what kind of topics do we study? For anyone who's interested in doing their own research into astro-particle physics and understanding it more, we study cosmology, so like the Big Bang, cosmic microwave background, dark matter, dark energy. We study high energy physics, so gamma ray bursts, pulsars, quasars, and active galactic nuclei. Active galactic nuclei are the black holes, They're the black holes at the center of galaxies. Super interesting. They deserve their own episode. We also study things like stellar and galactic physics. We study cosmic rays, so like the energy distribution of high energy particles from space. We study gravitational waves. Gravitational waves are super, 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 super interesting. Again, they deserve their own episode. I'm gonna do a whole thing about them. And multi-messenger astronomy, which is combining data from electromagnetic radiation, gravitational waves, and particles like neutrinos. So if any of these topics seem interesting to you, then please leave a comment and I will make specific episodes about these topics, like focus entirely on that topic, because like I said, so many of these things are super interesting. It does not do it justice for me to just very briefly go over it. And it needs technically it needs a very long time. It needs a lot of focus, but I guess we'd have to do just a 45-minute podcast episode. So, by now you might be wondering, well, Banan, all of the stuff that you're doing sounds super cool. You're studying the universe, it makes you like such a cool nerd. But what are you going to do with your life? What kind of job are you going to get with a master's degree in astro-particle physics? Well, then you're in the right place because I'm about to tell you. So, with a master's in astro-particle physics, you'll gain skills in both theoretical and experimental physics, which opens doors to various career paths. For example, which I think is the most basic example, research and academia. So you can go into PhD programs, you can work at universities or research institutes, you can become a postdoc or a lecturer studying topics like dark matter, gravitational waves. You can work at observatories or facilities like CERN, IceCube, LIGO. And again, you should do your own research on all of these facilities because they are pretty cool and the work they're doing is super, super interesting. Space and science industry, so you could work at space agencies like NASA and the ESA. The only thing that kind of sucks about this is because these are government facilities like NASA and the ESA, they will only accept, well, most of the time, let's not generalize, that's not fair. Most of the time, or most of the internships and job opportunities they have require you to be a citizen of that country, or they will at least give priority to students from that country. So there definitely are opportunities out there. You're just gonna have to look really hard for them. So here's to hoping that the Saudi Space Agency kind of grows, and because it kind of grows so that there are more opportunities for students like me in the physics world, so that I could go intern. Well, I think I'm too old for an internship now, but to kind of go work there and get actually like work experience and stuff. You could work on satellites and instrument design, so work on detectors and telescopes for space or ground-based observatories. Data science and analytics. You can work in AI and machine learning, technology and engineering. You could work in finance and consulting. A lot of my friends graduated with a bachelor's in physics and then went on to work for really big companies like McKinsey or PwC to work in consulting because, as a physics student, you have a very high level of math skills and critical skills and analyzing that you're a very good candidate to work in consulting. And last but not least, science communication and education. So you could work in science outreach, become a science communicator or educator, sharing knowledge through podcasts, writing or public talks. Because again, sharing awareness about science, showing the world how interesting it is a very important job. Education is very important. You teach physics and inspire the next generation of scientists. I think that's one of the most important jobs that you can have. And so the reason why employers value astroparticle physics graduates is because we have strong analytical and problem-solving skills, we have expertise in data analysis, programming, and modeling, we have experience with complex systems and large data sets, and we have the ability to approach big unsolved problems creatively. Think of astroparticle physics as studying the smallest ingredients of the universe. Things like neutrinos, photons, cosmic rays, and even dark matter particles. These particles travel across space and carry important information about distant cosmic events. Astronomy, at the same time, we use telescopes to study huge cosmic events like exploding stars, black holes, and even the Big Bang itself. These events produce the tiny particles that we detect here on Earth. So why is it cool? It connects the smallest to the largest. Imagine linking the tiniest particles, smaller than atoms, to the biggest structures in the universe, like galaxies and black holes. Astroparticle physics helps us do that. It helps us also in detecting invisible signals. So we can't see many of these particles like neutrinos or dark matter, but we built special detectors to catch them and decode their messages about the universe. It also helps us answer big questions like what is dark matter, this thing that makes up most of the universe's mass, how did the universe begin, and what happens when stars explode or collide. Why should we care? It's helping us solve some of the biggest mysteries of the universe, like how it started, what it's made of, and how it's evolving. Plus, it gives us tools and technologies that can benefit us here on Earth. For example, a lot of the cameras that we have on our phones, cameras in general, the original usage of cameras were as CCDs. So cameras that we have in our telescopes that we've been using for observation. So cameras originally started off as a tool, as an astronomy tool, and now we have them in our phones and we use them for everyday life. So when I was in my 3rd year, I did a project on the 3-body problem. What is the 3-body problem? So it's when two objects, like the Earth and the Sun, interact through gravity, and their motion can be described accurately using Newton's laws and solved with equations. This is called a 2-body problem, and their orbits are predictable and stable, which means you have the Earth's velocity, you have the Earth's position. You can always solve for where it's going to be. It's predictable. We can use these equations. It tells us how these two objects move. However, when you add a third object, like a planet orbiting 2 stars, the situation becomes far more complex. The gravitational forces between all 3 objects influence their motion, creating chaotic and unpredictable behavior. So in the first situation, we had the Earth and we had the Sun. Like we actually do have. And they're very predictable. It's a very stable celestial system. When you have a system of 3 bodies, for example, 2 suns and 1 Earth, or 2 suns and a planet, it stops being stable, it becomes incredibly chaotic, and it's very, very unpredictable. And this is called the 3-body problem. The main challenges of the 3-body problem is that it does not have an analytical solution. So there is no simple equation to describe the motion of all 3 objects over time, which means unlike the scenario where we had the Earth and the Sun, we cannot just have an equation, plug in the position, plug in the velocity, wherever at a certain time, and be able to solve for its position in the future. 3-body systems are also very sensitive to initial conditions, which means even a very, very small change in the starting position or velocities can lead to dramatically different outcomes. So because this 3-body problem does not have an analytical solution, so an easy equation that we can use to solve for these objects' positions, what I use in my research on the 3-body problem is, I guess we can call it a computer simulation. So in my research on the 3-body problem, using computer simulations and numerical integration techniques, which is something that you can look up if you're really interested in learning about, I use something called the Runge-Kutta method. That's a numerical integration technique, but I'm not going to go too much into it because it's too much, I don't want to get too technical on the podcast. But basically what I did 2 things. The first thing that I did was I put I put 2 stars and a planet in this system, in this computer simulation, and we usually use programming languages for these types of computer simulations. So for my research, I used Python. And what I did was I varied the initial conditions of the stars and the planet. Because like I said when you introduce a third body to the problem, then it becomes very sensitive to initial conditions, which means if you ever so slightly change the starting position or the starting velocity of these objects, then the whole system, changes. It's very, very highly sensitive. So the way that I want you to imagine it is, imagine you have two stars. Either these stars orbit each other in ellipses, or you have one star orbiting the other one, and then you've got the planet in the middle of these two stars. So it either kind of looks like a Venn diagram where their orbits intersect, or it looks more like a donut. There's a small ring that's one star, and the larger ring that's the orbit of the other stuff, and then the planet is in the middle. And so, like I said, the first thing that I did was vary the initial conditions just so that I can see how chaotic the system is. And then the second thing I did, I modeled my three-body system to the real-life Kepler-16 system, which is very similar in the sense where it's also two stars orbiting a planet. And for those of you who might not know this, there are other planets, there are other stars beyond our solar system. Yes, we have been able to detect them. We call these exoplanets. And so an example of a system like this, of an exoplanet system, is the Kepler-16 system, where it's a planet orbiting two stars, not just one in the case of our solar system. And so by modeling it after a real life system, I was able to sort of, compare between these. And I could find something called the habitable zone, which is where it's the region or the area where a planet would have to be in order for the planet to be habitable, right? So what does this mean? It means the planet has to be close enough to the stars where it's warm, but not so far away that it's cold, and not so far away that it no longer experiences the gravitational force of the star, and it keeps it in its orbit. I really hope all of this is making sense. So what am I trying to get at, right? Like, I feel like I'm just throwing a bunch of technical terms at you, and you're like, Banan, what are you talking about? Here's the cool part. There's a Netflix series called The Three-Body Problem. It's based on the famous sci-fi novel by Liu Cixin, and the story centers around a triple star system. So now it's three stars and a planet. And this planet faces utter chaos because of the star's unpredictable orbits. 1 minute it's scorching hot, the next it's frozen solid. So we're going back to this idea of stability. We're going back to the idea of the habitable zone that I also explored in my research, where it's like, okay, the planet has to be close enough to the star where it's like warm, life is able to thrive, but it's not so far away from the star where it's like cold, it doesn't experience the gravitational field, so on and so forth. And so the show premiered on March 29th, 2024, just 2 weeks after I submitted my paper. And I'm pretty sure there's no connection here. It is just very cool that I spent October 2023 to March 2024. The whole time when I was at school, I spent that time researching the three-body problem, creating computer simulations to research how is it having a planet in a two-star. We call these binary star systems, by the way, where it's one planet orbiting two stars. I spent 7 or 8 months researching all of this, researching the three-body problem, and then just 2 weeks after I submitted my paper, Netflix comes out with a show of the same name that was very critically acclaimed. A lot of people loved it, and I had friends and family texting me about it, like, we know that you've done your research on this. How cool is it that Netflix came out with a show about the same idea? And then they took it one step further. Instead of it just being a planet in a binary star system, a two-star system, it's a planet in a three-star system. And again, it's going back to this idea where when you have more than two objects in a system, it's chaotic, it's unpredictable, and we do not have the equations of motion to be able to, predict and solve for such systems. And of course, I watched the show and I enjoyed it from a purely science fiction perspective. I don't get my knowledge on math or physics or anything like that from Netflix shows, but it was definitely very entertaining to watch. And it definitely felt very good as I was watching the show to be like, oh yes, like, I've researched this, I've done this for 8 months of my life. It was like, this was a pretty big part of my life. And when you're doing such in-depth research on something, it somehow becomes a part of you, because even now it's been almost, it's been more than a year since I'd started that project. And, I'm a couple of months away from completing 1 year since I submitted it, and I'm still so, every time I hear the words the three-body problem, it's just, it has a special place in my heart. And I just think it's very cool that there's a Netflix show about the same idea. And it made it a little bit easier for me, because I remember a couple of times when, I would text my mom, I'd text my dad, I'd be like, oh hey guys, like, this is the latest draft of my computing project, please read it, let me know what you think. And my family, they're my biggest fans and I love them, but they're like, oh, we need a translator, we need a translator to be able to read your paper. And I'm like, okay. But when they watched the Netflix show, I think it made a lot more sense to them, and they were like, oh, this is what you were doing, like, that's so cool. So Netflix really did help me out. It made my life so much easier when I was trying to explain to people what I was doing my computing project on. And that's it. That's all we have for today. I tried to answer as many questions as possible. I hope, to my family, who I dedicate this episode to, just because they're the most supportive and loving people out there. I hope you now understand better what it is that I've been doing for the past 3 years, what it is that I've been doing in Zurich for the past 3 months, just because it's close to the end of term now. And yes, if you have any questions, please let me know, and don't forget to follow this account, follow the podcast account, and hit the little bell button so that you get a notification every time I upload a new episode. Thank you for your time, and I hope you enjoyed.